Have you ever wondered what truly keeps planets orbiting the Sun, or what bends the light from distant galaxies? The answer lies in one of humanity's greatest intellectual achievements, Albert Einstein's theory of general relativity. More than just a dry mathematical formula, this theory has redrawn the picture of the universe, from how gravity works to the evolution of space and time itself. Join us as we explore how Einstein deciphered the universe's deepest mysteries, revealing that space is not just a static backdrop, but a dynamic entity that bends and warps, creating the phenomena we call gravity. This is not merely a physical theory, but a new lens through which to view our entire existence. Welcome to SpaceTime's cosmic journey, where we explore the universe's deepest mysteries. In this video, we'll delve into the topic, Einstein's general theory of relativity, how the universe operates. Don't forget to subscribe to our channel so you don't miss out on other exciting cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us. Before the advent of general relativity, gravity was described by Isaac Newton as a mysterious force acting instantaneously between distant objects. Newton's famous formula was remarkably successful in predicting planetary orbits and explaining the fall of objects on Earth. However, it couldn't explain some minor phenomena, and most importantly, it was incompatible with Einstein's own special theory of relativity, which had already revolutionized the concepts of space and time. Special relativity, published in 1905, revealed that space and time are not absolute, separate entities, but two sides of a coin called SpaceTime. It showed that the speed of light is an absolute constant in all inertial frames of reference, leading to astonishing consequences such as time dilation and length contraction when objects move at speeds close to the speed of light. But special relativity only applies to inertial frames of reference, that is, systems not subjected to acceleration. Gravity, by definition, creates acceleration. So how could gravity be integrated into this new theoretical framework? This was the challenge Einstein set for himself over the next 10 years, leading to the birth of general relativity in 1915. The core concept of general relativity is the equivalence principle. This principle states that there is no way to distinguish between an accelerating reference frame and a reference frame in a gravitational field. In other words, the sensation of being pulled down by gravity is identical to the sensation of being pushed into the back of a seat when a car accelerates. To visualize this, imagine you are in a completely enclosed elevator. If the elevator is stationary on Earth, you will feel gravity pulling you down. If this elevator were taken into deep space, where there is no gravity, and pulled upward by a rope, with an acceleration equal to Earth's gravitational acceleration, you would also feel pulled to the floor in the same way. These two states are indistinguishable. From the equivalence principle, Einstein deduced that gravity is not a pull between two objects, but rather the manifestation of the curvature of spacetime caused by mass and energy. This completely changed how we perceive the universe. Instead of planets being pulled by the sun, they simply follow the shortest possible curved paths in the spacetime already distorted by the sun. Imagine a flat, stretched rubber sheet representing spacetime. If you place a heavy bowling ball on the sheet, it will create a depression. If you roll a small marble near the bowling ball, the marble will not travel in a straight line, but will be drawn into a curved orbit around the bowling ball. Similarly, the sun, the bowling ball, curves spacetime, the sheet, and the Earth, the marble, moves along this curve. This explains why all objects, regardless of their mass, fall with the same acceleration in a given gravitational field in a vacuum,
neglecting air resistance. This is because they all follow the same curve in spacetime.
General relativity provides a complex field equation that describes the relationship between the distribution of mass and energy in the universe and the curvature of space-time. This equation, also known as Einstein's field equation, is the heart of general relativity and one of the most beautiful equations in physics. One of the earliest and most important predictions of general relativity was the bending of light by massive objects. According to Newton, light has no mass and therefore should not be affected by gravity. But if gravity is the curvature of space-time, then light passing through a curved region of space-time must also follow that curve. This prediction was spectacularly confirmed in 1919 by astronomer Arthur Eddington. He observed the apparent shift in position of stars near the Sun during a total solar eclipse, exactly as Einstein had predicted. This event propelled Einstein to global scientific icon status. Another prediction was the precession of Mercury's perihelion. The orbits of planets around the Sun are not perfect ellipses, but undergo a slow shift. While Newton's theory explained most of this shift, it couldn't account for a small remaining portion for Mercury. General relativity precisely explained this missing part, providing strong further evidence for its correctness. General relativity also predicted the existence of gravitational waves, ripples in space-time that propagate at the speed of light, generated by the acceleration of massive objects. Typical examples include the collision of black holes or neutron stars. Although Einstein himself doubted the possibility of detecting them, modern technology has allowed us to do just that. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves originating from the merger of two black holes billions of light-years away. This discovery not only confirmed a major prediction of Einstein, but also opened a new era of astronomy, allowing us to hear cosmic events instead of just seeing them. Black holes are one of the most fascinating concepts predicted by general relativity. When a very massive star runs out of nuclear fuel, it can collapse under its own gravity, creating a region of spacetime so curved that nothing, not even light, can escape. The boundary beyond which nothing can escape is called the event horizon. Inside the event horizon, theoretically, lies a singularity, a point of infinite density and spacetime curvature. Although there is still much debate about the true nature of singularities, black holes have become an indispensable part of our understanding of the universe and have been observed indirectly through their influence on surrounding matter. General relativity also provides the foundation for modern cosmology. It allows us to model the evolution of the universe on large scales. Solutions to Einstein's equations led to the Big Bang model, which describes our universe beginning from an extremely hot and dense state, then expanding and cooling. The expansion of the universe is not galaxies moving away from each other in a static space, but rather space itself expanding, carrying the galaxies with it. Evidence for this expansion was discovered by Edwin Hubble in the 1920s, when he observed that distant galaxies were moving away from us at a speed proportional to their distance.
General relativity also plays a crucial role in understanding the cosmic microwave background, or CMB radiation, a faint afterglow from the early universe. The CMB is one of the strongest pieces of evidence for the Big Bang model, and is a picture of the universe when it was about 380,000 years old. Furthermore, general relativity raises profound questions about the existence of dark matter and dark energy. When applying Einstein's equations to astronomical observations, scientists found that there is more mass and energy in the universe than what we can see. Dark matter is believed to provide additional gravity to hold galaxies together, while dark energy is thought to be the cause of the accelerating expansion of the universe. These mysteries, although not directly explained by general relativity, this theory itself has provided the framework for us to ask those questions and seek answers. It is a powerful tool to explore the limits of our understanding. General relativity is not the final theory. It is not fully compatible with quantum mechanics, the theory describing the world at atomic and subatomic scales. Unifying these two theories into a theory of everything remains one of the greatest challenges in modern physics. Practical applications of general relativity include the Global Positioning System, GPS. GPS satellites orbit Earth at a certain altitude and move at high speeds. Thus, they are affected by both special relativistic effects, time dilation due to speed, and general relativistic effects, time dilation due to gravity. Without accounting for these effects, the GPS system would accumulate significant errors, making positioning extremely difficult or inaccurate.
Specifically, clocks on GPS satellites run approximately 45 microseconds faster per day due to weaker gravity, according to general relativity, and approximately 7 microseconds slower per day due to high speed, according to special relativity. In total, satellite clocks run about 38 microseconds faster per day compared to clocks on Earth. Although only microseconds, this error would accumulate to kilometers per day if not corrected, rendering GPS useless. Therefore, general relativity is not just an abstract concept, but an indispensable part of our daily technology, helping us not get lost and maintaining a connected world. It demonstrates the power of scientific thought and humanity's ability to discover the deepest laws of the universe. General relativity continues to be a vibrant field of research, with scientists constantly seeking new evidence, testing its predictions, and exploring the theory's limits. From studying supermassive black holes at galactic centers to tracking gravitational waves from dramatic cosmic events, each new discovery enriches our understanding. It has permanently changed how we perceive gravity, space, time, and the universe. From a mysterious force, gravity has become a geometric property of SpaceTime. The universe is no longer a static stage, but a dynamic entity, bending and warping according to the presence of mass and energy. Einstein's ideas, though seemingly complex, have become the foundation for most modern astrophysics and cosmology research. It is a testament to the ability of an extraordinary mind to unveil the deepest mysteries, challenge preconceptions, and open new horizons for science. We have come a long way from ancient notions of the universe. General relativity has brought us closer to a more comprehensive and accurate picture of how everything operates. It reminds us that the universe still holds countless things to explore and understand, and each answer opens up even newer questions. General relativity has shown us that space and time can be warped, and that's how gravity works. But are there other fundamental rules governing our universe that we cannot change? Are physical constants like the speed of light or Planck's constant fixed values, or could they have been different in the past, or will they be different in the future? In our next video, we will delve into the world of physical constants, understand their role in shaping reality, and ponder the challenging question, can we change them? Don't miss it.